Welcome all of you. This is the NPTEL discussion session for January to April 2025 batch. The course name is Finite Element Method, and I am the TA of this course. The course instructors are Professor Biswas Banerjee and Amit Shaw. Both are from the IIT Road, Kharagpur. And I am Nikhil Gupta. I am a research scholar in Department of Civil Engineering in ISC Bangalore. So this discussion session will be conducted on Saturday 3 to 5 p.m. And if any doubt, you can directly write to the forum also, or you can ask here also. And this is the first week class, which is on 21st of January. So let's start. So actually, what is the purpose of this TA session is means to clarify your doubts, and whatever doubts you can have, you can ask here. And how I'll conduct it, that I'll do the problem solving sessions. I'll get you the different questions which will be helpful for your future assignments, and I'll not solve the assignment which is due, but yes, I'll solve the related questions which will be helpful for you all to go to the assignments. So since this is the first week, you don't have the assignment date is not passed yet, so I won't discuss these assignment questions. But yes, if you attend this class, you will get a gist of how to solve the assignment 1 problems. Also, initially I'll go to the theory of FEM with the very basic of it, so that you can start with it. So let's start. So also these sessions will be are recorded and will be uploaded in the YouTube channel. You can directly visit there, and you can revisit it and have a look on it and revise it. So what is actually FEM is? You have attended one week session. Can anyone unmute or write in the chat box what actually FEM signifies to you? Anyone? Okay, no problem. So what FEM is, I'll write. FEM is a method to solve differential equation. Now you have a question, you may have a question that we have a different methods to solve differential equation. Maybe directly we can solve how we have studied in differential equation chapter in mathematics, or we have learned different numerical methods like backward Euler, forward Euler. So why we need this FEM? So this is for this. I can tell you that the complex problems which you have to solve, which are not which are very costlier and not able to solve with the numerical method, that will be very helpful for solving the differential equation by FEM. So why only differential equation? Means what is the significance of the differential equation? So to tell you that we have seen various physical phenomena are derived from differential equations only. Like if we see the EI d2y by d4y. So the physical phenomena d4y by dx power 4 equals to wx. We know this is the general form of a beam equation. Also, we know the equation like EA d2y by dx square is equal to wx will signify you the axial loaded bar. So this shows you how physical phenomena are derived from the differential equation, and to get to the results of it, we need to solve this equations, and these differential equations to get to know how these methods are behaving, how these physical phenomena are behaving. So what differential equation is generally known as its boundary value problem. So the boundary value problem consists of differential equation plus the boundary conditions. So this signifies that FEM can be used to solve the boundary value problems. So if we tell you more about it, the physical phenomena, so we can write physical phenomena which can be solved includes conduction, where our unknown variable can be temperature. Then we can have torsion of elastic shafts. Then we can have diffusion also. Also in water resource, we have studied groundwater flow. That also can be solved. Also in structural, we have studied elastic behavior. So it can be utilized for 1D, 2D, 3D, maybe beams, maybe plate or shells. So this shows you how diverse FEM is and how you can use in practical problems for solving it. So what we do in FEM, we discretize the problem. I'll further make it clear. So first step is to discretize the finite element. Discretize the finite discretize the element the whole structure into finite elements. So if you see, let's take this as a bar. This is whole of your beam, or we can say axial loaded bar also. So let's see, we are increasing the temperature or and heat conduction is happening. So for heat conduction problem, our we know that our unknown variable is temperature. So let's say at this point this is T1, at this point this is T2, at this time it is T3, and this time it is T4. So what we are doing, we are discretizing this whole bar into this points. So this is first, this is second, this is third, this is fourth. So these four are the nodes which are the parts of these elements, and the nodes collecting elements, the space between these nodes is known as the elements. So here we have four nodes and three elements, and when we and at a certain point or time, if we see the temperature of at each of the node is T1, T2, T3, T4. So when we solve a finite element method, we can maybe assuming a linear interpolation, we'll get a curve like this. But we don't know that in originally this is forming a linear interpolation or not. So if we see, if when we solve it, we can get a curve like this. Oh, sorry. So we can we'll get a, so it can follow any curve. So this is your exact solution, and the black one is your FEM solution. So what we notice in this, we see there is a gap between the exact solution and the FEM solution. So this means that at nodes, since they are crossing at the same points, we see that the at nodes FEM provides us the, so there is a gap between it, which shows that the FEM solution is not exact at that point. So when we So how to get to the exact solution from FEM? There are two methods to get to the exact solution in the FEM. One is known as P refinement and other is H refinement. So what we do in this two, there are two methods. Means since this is your bar, what we can do, we can, let's see, we have taken three elements and four nodes. One, two, three, four. These are four nodes and these are one, two, three elements. Now, if we can do two things, that we say that these temperatures are varying cubic or square parabola. So in that case, we are refining it into higher order solution, and this is known as P refinement. Means if we are initially, let's say we were assuming the variable as u plus a naught plus a1x. Now we will take it as a naught plus a1x plus a2x square. So this suggests that we have assumed a higher order a higher order field variable. So to get to the exact solution. Other is H refinement. In that, what we will do, we can do higher number of nodes. Means we can do it like this. We can increase the number of nodes. See, 1, 2, 3. Now what you'll see, you'll get the exact solution at this point. And if we assume it as linear also, it may behave in a similar way. So if, let's say, exact solution is like this, so since the interval is too less, the error is also reduced. Now I'll tell you how this thing happens. Means if you see the graph of number of elements and displacement, we see, let's assume this is the exact curve. As we do a mesh refinement in this direction, the FEM solution will increase, and at some time it will reach to the exact solution. How is it reaching the exact solution? Let's say our original result, means exact solution, follows a naught plus a1x plus a2x square plus a3x cube. Let's see, let's assume that our solution is having cubic solution, and initially we have assumed it as in FEM as a naught plus a1x. So it won't give a exact result, but it will show you a higher error. Similarly, at a point at which you assume it as a cubic, means you are increasing the number of elements or mesh refinement, you will reach to the exact solution. And for this we know that the FEM solution are lower bound, not the upper bound. So the main equations what we observe in FEM is, you all have heard it, is KD is equal to F. What this is? This is the stiffness matrix. You must have studied in the matrix method in undergrad. So this is stiffness matrix. This is displacement of nodal vector, displacement nodal vector, and this is the force vector. So the main thing is how the dimension of this K matrix is determined. So this K matrix dimension is equal to number of degree of freedom of the structure. So you must have seen the questions in your assignment where number of degree of freedom or the dimensions of the K matrix are being asked. So you just have to find the number of degree of freedom to get the stiffness matrix dimensions. So let's start solving uh, a 2D truss element. So let's take 2D truss element. Okay. So I'll not solve the. I'll give you a generalized formula for it so that you can use anytime. I'll not take it as a horizontal or a vertical member. Let's say this is your x and y axis, and your bar is like this, whose length is L. This node is I. This node is J, and let it be at angle beta. So let's assume A as the area of cross section, E as the modulus of elasticity of this bar, and so so if we calculate the sine beta, let's calculate the initial part with the sine beta and cos beta because we'll using all this. So this will be yj minus yi divided by L. Similarly, cos beta is xj minus xi divided by L. So let's, for our simplicity, take it as S. For this, we'll take it as C for sake of simplicity of writing. Now, for every structure to generate K means stiffness matrix, we have to activate one of the degree of freedom at a time, and all other making it zero. What this means, since this is our bar, these are our degree of freedom: uj, vj, ui, vi. And remember that you have to take FEM degree of freedoms in positive direction. Now, since you have written the degree of freedom, what next is, you have to activate one of the degree of freedom what I have written. So let's activate UI. This was our initial. When you, this is the UI in the x direction, so when you push it to the direction, this bar will become like this. Now this is your I, this is your J. Since it has said that activate only the one of the degree of freedom and at the time all other zero, so since all other are zero, you see I have made this not change. So this degree of freedom will not change its point, but I have already changed, and Vi is also not changed. So now you see this deflection which we have got is Ui, which is very small. And if you take a perpendicular to this deformation has occurred in it since we are pressing it down. So so this is old I, this is new I, and now if you see, this will be cos of ui. So axial deformation which has occurred is cui, which is this. Initial length was full this, now it has reduced to this, so axial deformation of cui has occurred. Now if you see, the force which is acting on it will be now so we know sigma by epsilon is E. So force which is acting is AE delta L by L. So if we solve it, delta L by L we know is the deformation. So AE, how much it has deformed is AE into CUI divided by total L. So what we if we see in x direction is AE by L C square UI, because we are multiplying for x coordinate, we'll multiply with cos theta. For y component, we will multiply by sin theta. So it will become CSUI. To remind you, that C and S are the cos theta and the sin theta, sin beta, which we have mentioned initially. So similarly, if we see in the problem, when these forces are applied in these nodes, similar reaction force will be acting at this point, which we say that it is acting because we are not allowing it to move. So since we are not allowing it to move, this node will uh, also have a reaction to it. So when you see the reaction of it, you will get at node J fx as minus of ae by l c square ui, and fy is equal to minus ae by l cs ui. How I got this? This will be same in the x direction and y direction, just the opposite of the sign. This is because you have to maintain the equilibrium of this bar, and x direction and y direction forces will be balanced. So after getting this, first column of k can be written as ae by l c square cs minus c square minus cs. So if we write in the full kd is equal to f form, we can say this ae by l c square cs minus c square and minus cs will be equal to, oh sorry, ui will also be there. Ui equals to fix fiy fjx and fjy. So right hand side is the force vector which is acting externally in the structure. So since this we have done for one of the element, means this is done for one of the element. When we increase this for more of the element, means we have activated u1 here. If you see, we have activated u1. Similarly, we can activate u2 also, uj also, vi also, vj also. When we do the same thing, our k matrix will become ae by l. I'll write for all degree of freedoms. C square cs minus c square minus cs with cs s square minus cs minus s square minus c square minus cs c square cs minus cs minus s square cs and s square. This is the k matrix you have got. Now this is the elemental stiffness matrix. This is known as elemental stiffness matrix. Why this is known as elemental stiffness matrix? Because you are solving for one of the element. You have taken a structure, you have taken out one of the element of it, and you are solving for it. So for one element, this is the k matrix you have got. Now how to now if you see a question is in your assignment, you will simply get an answer by using this matrix, by using the changing the beta and all. So how to assemble the matrix for global, to get the global stiffness matrix? Let's say uh, you have this truss, we have solved for one of the element. Now let's say this is let's say two elements. Now this is 1, this is 2. Let's say this is 1, this is 2, this is 3. This is element 1, this is element 2. This is U1 V1, U2 V2, U3 V3. Now let's say we'll take a one of the element, we'll take the first element, and when you will solve it, you will get a K matrix which will be related to U1 V1 and U2 V2. Similarly, the row will also correspond to U1 V1, U2 V2. Now, when you take a element number 2, when you take this element and form a matrix, K matrix, that will correspond to U2 V2 and U3 V3. Similarly, in row, U2 V2 and U3 V3. So to combine this matrix, what we'll do, we'll add the common members, and our final K matrix will be U1 V1, U2 V2, U3 V3. Similarly, in rows, U1 V1, U2 V2, U3 V3. And the members which belong to U2 and V2 will be the sum of these members and this members. We'll add this member and we will put a summation here, and we'll get a global stiffness matrix. So remember the name, this is global stiffness matrix. So wherever in the question you are being asked to get the elemental stiffness matrix, remember that you have to find the stiffness matrix for one of the element, and if you are being asked to find out the global stiffness matrix, you have to find the stiffness matrix for whole of the structure, and by adding all of the members. So let's do a question. Just read a question and try to read it and get to this solution. I'll give you 2 minutes. Anyone who can tell me how to approach? Okay, no problem. I'll tell you. So since we know, now see the question what it is asking. Choose the correct stiffness method for AD. Now you have to find the stiffness matrix for element AD. Since it is asking for element AD, you know that this is the elemental stiffness matrix which you have to calculate. Now, as we have studied that K matrix is AE by L, and now also one thing that this is a truss, so it will have a two degree of freedom at each of the node. So when you form a stiffness matrix, I have told you C, which is cos square theta, cos theta, sin theta, minus cos square theta, minus cos theta, sin theta. Then here it will be cos theta, sin theta, then sin square theta, then minus cos theta, sin theta, then minus of sin square theta. This will be cos square theta minus cos theta sin theta, cos square theta, and cos theta sin theta. Similarly for last thing, cos theta sin theta minus of sin square theta, cos theta sin theta, sin square theta. So this is the elemental matrix which we have studied, and since it is at a certain angle, it will give you the same thing. Now you have to compute for this member AD. Now let's calculate L first. So length of AD we are calculating. Length of AD. This is A, this is D. Now it is written 2L here, 2L here. So we can get that this theta is 45 degree. So the length of AD will be, we know the Pythagoras theorem, we will get 2L root 2. Write it properly. 2L root 2. So since theta is 45, we can say cos theta is equal to sin theta, which will be equal to 1 by root 2. Similarly, since we have to use different values of cos square theta, we'll calculate is at 1 by 2, which will be same as sin square theta, and cos theta, sin theta will also be same. So now just we have to, what we have to do, we have to put the values in this elemental stiffness matrix. So this K is equal to AE 2L by root 2 1 by root 2 1 by root 2 minus 1 by 2 minus 1 by 2 1 by 2 1 by 2 minus 1 by 2 minus 1 by 2, then minus 1 by 2 minus 1 by 2 1 by 2 1 by 2, then minus 1 by 2. I got it. Only please show me last page once, please. Okay, see this. I'll wait for 2 minutes to have a look. Let me know if I am too fast, so that you, and anytime you can ask me the doubts if you have any problem in this. Okay, so we'll make, okay, now we'll continue. This is minus 1 by 2 1 by 2 and 1 by 2. So when we simplify it, the K matrix what we'll get is AE divided by 4 root 2 L 1 1 minus 1 minus 1 1 1 minus 1 minus 1 minus 1 minus 1 1 1 minus 1 minus 1 1 1. So can anyone tell me this is elemental stiffness matrix or global stiffness matrix? Anyone can, if you not want to speak, you can write also. Is it elemental or global stiffness matrix? Sure. Aryan, you are right. So why this is elemental? Because this is, you are finding it for one of the element. So if we have to find global stiffness matrix, what we have to do? We have to find for all this AED, AAE, and then make it a summation on each of the different degree of freedom and get to the global stiffness matrix. Now, yeah, now let's go to the second question. So this question is little big. What I have done, I have make a full question of FEM. So starting from the stiffness, forming a stiffness matrix, then discretizing the and assembling and finding the boundary conditions and the reaction forces also. This is the full question we will be solving. I'll give you a 2 minutes to have a look on the problem so that you can get what it is. Read one time, then we'll start solving it. I'll zoom it so that it is visible for you all. Okay. So this is a simple truss problem. Initially we'll start with the formation and then find everything. It's a full problem of on FEM. Okay, so let's start solving it. So you remember the first step in forming the stiffness matrix. The first step is removing constraint. When you remove the constraint, our truss will look like this. I'll take it this as straight. Okay. So what we have to do, we have to discretize the elements. So this is node 1, this is node 2, this is node 3. When this is node 1, then let's take this is first element, let's take this is second element, let's take this is third element. And now you have to tell what are the degree of freedoms. So since this is a truss element, every node will have a 2 degree of freedoms. So this node will take as u1 v1. This is u2 v2. This is u3 and v3. Now let us take member 1. When we take member 1, we have to form a elemental stiffness matrix. What member 1 is, we'll form a free body diagram. This is member 1 where we are getting it. This is node 1, this is node 2, this is v1, this is u1, this is u2, this is v2. Now and let's say with the question what it is given, if we calculate AE by L, we'll get a 100 by 10 is equal to 10. The values are given in the question. You can get to the video and calculate that. If not, we'll assume it like that. Okay, so let's form the elemental matrix of K1. When you form this, you know outside is AE by L, so 10. Now for convenience, you can write at up that this is U1, V1, U2, V2. Now this side also u1 v1 u2 v2. So what this u1 in the column and u1 in the row signifies that the column 1 is that what you are giving the you are increasing the unit displacement in that direction, and if you have the coordinate at which you are calculating the force due to the displacement at u1 is on the row side. So when you calculate, when you use the same formula which we have used here, you see that the it is horizontal. So some horizontal, so some part will be 0. So what you will get, one part will be 0, one part will be 1. So what you will get is like this. So when we put theta is equal to 0 in this equation, we'll get this stiffness matrix. So similarly, since this is the elemental stiffness matrix of one of the member, we'll do similar thing for vertical bar as well, which is member 2. So this is member 2. So for this, the nodal values are 2 and 3, where you can take this is as u2, this is v2, this is u3, and this is v3, which we have assumed only also. So now the stiffness matrix of K2 will be, for convenient, we'll again write u2 v2 u3 v3. Similarly u2 v2 u3 v3. So now if you see, the angle now is 90 degrees. Since the angle is 90 degree, it will be reversed, and this values will be 0. This is 0 1 0 minus 1 and 0 0 0 0 and 0 minus 1 0 1. Okay, so this is done for the second of the element. Now we'll form a elemental matrix for member 3. So now the general case which we have solved with inclined 1, this is member 3, this is node 1, this is node 3, this is u3, this is v3, this is u1, and this is v1. And we have already calculated the angle. It has angle is 45 degree, because length is 10 here, 10 here, so this angle is 45 degree. Now we have studied the general form of this elemental matrix. So when we'll form it, we'll write here u1 v1 u3 v3 u1 v1 u3 v3. Now when we put it, we'll get 0.5 0.5 minus 0.5 minus 0.5 0.5 0.5 minus 0.5 minus 0.5, then minus 0.5 minus 0.5 0.5 0.5 minus 0.5 minus 0.5. This will be 0.5 and 0.5. So now we have elemental matrix for all of the three members. Now what we have to do, we have to assembly this these elemental matrix to get a global stiffness matrix. So now what we'll do, we'll assemble the elemental stiffness matrix to get global stiffness matrix. Now you see, simple thing is that initially you write here u1 v1 u2 v2 u3 v3. Similarly in row also u1 v1 u2 v2 u3 v3. Now what you have to do, you have to see the elemental matrix corresponding to each of the degree of freedom you have mentioned here and here, and we'll calculate. See, so what corresponded to u1 on v1? Let's see. So when we have taken member 1, u1 is there, v1 is there, u1 is there, v1 is there. This means this will contribute. Other thing, here it is no u1 v1, so it will not contribute. Now in this, yes, u1 is there, v1 is there. So these u1 and v1 value will be added. So here it is 1, outside is 10. So this will give you 10, and from there here you will get 0.5. I think I have missed A by L. So in this it will be A by L is 20, and this also it will be 20. Yes, it will be 20. This will be 10 because it will come by 2. So wait, this will be, member 2 will become as 5, because the it depends on the length of the member. So this A by L is coming as 5, this A by L is coming as 20. So when we do a global stiffness matrix, we will see that in member 1 we are getting u1 v1, so this is 10, this is not there, in this it is 10. So the first member will be 10 plus 10, which will be 20. So similarly u1 v1, let's see this member u1 v1. When you see this member, you will get in the first one, this is u1 v1, this is 0, and this is 20 into pi is 10, so you will get a 10 value. You just have to add them. So 10. Now let's start with do one more, which is v1 u1. Let's see where v1 u1 is acting. In the first member v1 is there, u1 is there. Okay, so this you have to take. This is 0, no problem. Else this is V1, this is V1, this is U1. 0.5 into 10 into 20, it will give you 10. So you will get here 10. Is it clear with everyone? I've got a message. How we get 0.5? Okay. So this 0.5 we have got by this formula. This is cos square theta. So cos square theta is there. So cos square theta we have seen for this member, since 45 is there, so you will get cos square theta is 0.5. Similarly, when you put cos theta sin theta, then also you will get zero point 0.5. This also 0.5, this also 0.5. Since this is 45, all will be 0.5. And similarly, when you have got this value, so I have written by substituting the theta value as this. I hope this is clear for you. Since the same question is there, that we have calculated on only this. Now your angle is 45, so we have directly substituted the theta value as 45, and 45 all cos theta will be and sin theta will be same, so it gives you 0.5 for all. So now we are adding. Now let's do one two more check. Let's take a random thing. Let's take V2 and V2 and V2. Let's calculate V2 and V2. Let's go to member 1. Is there V2 is there? Yes, V2 is there. Is there V2 is there? Yes, V2 is there. But V2 and V2 giving you 0. So not a problem. Then is V2 is there? Yes, V2 is there in member 2. V2, then V2 is giving you 1 into 5. This should go to 5. V2 and V2. Now let's see, is there V2 is there? In this V2 is not there. So this was coming as, wait, this V2 and this V2. So when we'll go to V2 and V2, so this is getting 0. This is getting 5. This is getting V2 and V2. We are getting it as 5, and here no V2. So V2 and V2 will get 5. We have just have to add. Similarly, if you do for all of this, you will get this. You can later solve it and get to the solution. It's easier. If someone is having doubt, I can take more of it and show you how it is being done. So V2 is now 1 2 3 done. This is 0, this is 0, this is 0, 5, 0, minus 5, minus 10, minus 10, 0, 0, 10, 10, this is minus 10, minus 10, 0, minus 5, 10, 15. So I have directly written this, but if you get a time, just look into it, the problem. If you still have a problem, do ask me in the next session. I'll clarify. So now this K matrix is being done. Let's see what question says the next thing. So it says apply the displacement boundary conditions and solve the reduced system for unknown degree of freedoms using Gaussian elimination. Okay. So to write it in Ku is equal to F forms. This is K matrix. Okay. What this U will be? This will be U1, V1, U2, V2, U3, V3, and F will be Fx1, Fy1, Fx2, Fy2, Fx3, and Fy3. These are the external forces which are applied in the beam in the truss. So is there any external forces? Yes, there are. Where it is? This is 2 unit and this is 1 unit. So what we have assumed? We have assumed U1 V1 here, U2 V2 here, U3 V3 here. So this will be F3x and F3y. So you have two values of external forces. So we can replace it. We can write here, this is fx3 is what it was 2 and this is 1. I'll show you again. See, this fx3 is 2 and fy3 is 1. We can replace this now. Let's go to now. If you now one more thing to observe in this K matrix. Let's see the summation of each of the column. This is 20. This is 20. This is 10. This goes to 0. This is 30. Then this is 30. Plus 30 and minus 30. So you see all rows are getting 0. Means 10, 10, 20 and then minus 20. So it is 0. Similarly, this is 0. This is 0. This is 0 and this is 0. Can anyone tell why these are being 0? Yeah, and is it singular matrix or not? Anyone? Think the initial one thing which we have done in this problem. Initially, what we have done. Is it a singular matrix or not? And if it's singular matrix, can we solve it? I'll wait for 2 minutes to think for you. Just have a look and think of it. So the answer is yes, the matrix is singular, so we can't solve it directly. But the question arises, why K matrix is coming singular? So the answer is this. Remember initially what we did? We have removed the constraints and formed this K matrix. Since we have removed this constraint, now what will happen? Now what will happen? Your truss, which was how was it truss? Your truss is like this, and it can, since no constraint is there, it can move in this direction, it can move in this direction, or it can rotate as well. These three are known as rigid body motions. There are too many rigid body motions existing in a structure, but three are only independent, linearly independent. So if we reduce all three in the K matrix, we'll get a reduced K matrix which can be solvable. So if you see, what are the constraint we have got in the problem? You see, this is one constraint, this is one constraint, this is one constraint. Now see, putting these three forces, the external forces, the truss will not move like this, or nor it will rotate also. So if we reduce all these three forces in the matrix, we'll get a reduced stiffness matrix. And what are these? These are V1, or we can take this direction. So we get, this is U1 and this is V2. Let's see. Now you know that also when we apply a boundary condition, we can say this is 0. We can say this is 0. This is 0 because we are putting it. So when we got this, we can say uh, U1, V1 and V2. So U1 is 0, V1 is 0 and V2 is 0. So let us form now. I'll make a full matrix again, which is 20, 10, minus 10, 0, minus 10, minus 10, 10, 10, 0, 0, minus 10, minus 10 and minus 10, 0, 10, 0, 0, 0, then 0, minus 10, minus 10, this is 0, this is minus 10, this is minus 10, 0, 0, 0, and 5, 0, minus 5, 0, 10, 10, minus 5, 10, 15. Okay, so this is u2, v2, u3, v3, and then the fx1, fy1, fx2, fy2, fx3, fy3. Now you have seen that these two values we know, so we can directly write it as 2 and 1. Also we have seen that this u1 is v1 and u2, so this will go up to, this is 0, this is 0, this is u2, and this is 0. I hope you have understood the values which I have put. I'll wait for 2 more minutes so that you can get, if you have a doubt you can ask. Okay, no problem. If no doubts, I'll move forward. So since we have taken 3 of the rigid motion, body motion capturing, so what we'll do, we'll remove this row, we'll remove this row, we'll remove this row. Correspondingly, 1, 2, and this we'll remove, because this was also u1, this was v1, this was u2, this was v2, u3, and v3. Correspondingly, we have removed. Now what we'll get, we'll call it as reduced stiffness matrix. So the term comes reduced stiffness matrix. So what it will be there, this will be 10, this is 0, 0, 0, 10, 10, 0, 10, 15. Okay, so what you got, we have got this 10, 0, 0, 0, 10, 10, 0, 10, 15. Now we'll take this as u2, u3, and v3 equals to 0 to 1. Okay, so this is the final ku is equal to f matrix, which can be solvable using a method. Maybe one of the method is Gauss elimination method, which is asked in the question. See, it is written, solved it by Gauss elimination. So before solving with by Gauss elimination, you have to make sure that the K matrix is non-similar. So here you have got a non-similar matrix of K. Now what you will do, now you have to make it as a upper triangle matrix. So what you will do, you will transform it as R3 as R3 minus R2. So what it will give you, 10, 0, 0, 0, 10, 10, 0, 0, 5, then u2, u3, and v3. Wait, okay, correct, R3 minus R2. Okay, so we have done a matrix thing. Now if you solve it, you will get 5v3 equals to minus 1, and v3 will be minus 1 by 5. Similarly, you will get u3 as 2 by 5 and u2 as 0. Okay, so these are the final solution you will get is what you have computed. You have computed using FEM that if you apply this loading in a truss like this, what deflection will occur at each of the node. You have got that. So as we know, it is U2 or U3. Which one? Let me check. U2 or U3. U2 is this and U3 is the. So U2 is there, na? U3 should also be there. Let me check. Mm, this will be U3, na? U3 will come. This is U3. But I think U2. U2 is also there, U3 is also there, and V3 also there. U2, U3, and V3. Since U2, U3, and V3 are the unknowns. If you see, this U2 is unknown, U3 is unknown, and V3 is unknown. Rest you have taken at 0. So U2 is also there and U3 is also there. So when you have computed this, we have got U2 as 0, U3 as 2 by 5, and V3 as minus 1.5. Okay. Now the next question, next part of the question, which says recover the nodal forces of all joints including reactions. Now we have to calculate the reaction forces. Okay, the next part of the question says to calculate the reaction forces. Now let's take this is K matrix. I have to make it again. This is 20, 10, minus 10, 0, minus 10, minus 10. Then this is 10, 10, 0, 0, minus 10, minus 10, minus 10, 0, 10, 0, 0, 0, then 0, 0, 0, 5, 0, minus 5. Okay, then minus 10, minus 10, 0, 0, 10, 10, minus 10, minus 10, 0, minus 5, 10, 15. This is the K matrix, original K matrix which we have got. Now what we have computed? We have computed U1 as 0, V1 as 0, U2 as 0, V2 as 0, and this is 2 by 5 and this is 1 by 5. I'm just putting the values we have calculated. Now if you see the right hand side is the external forces which we are having for 2 and 1 only. But if we see the main problem, there is a there will be a reaction, means here Rx1, here Rx, Ry1, and there will be Rx1. Similarly, here only one will be there, which will be Ry2. So what will write here? This will be Rx1, Ry1, then 0, then Y2. Why this is 0? This is because if you see it is moving in this direction. There is no reaction force acting in this direction, so it is 0. Okay, so now you see you have to calculate these three values from using the last calculations. We have reduced the matrix and we have got the U2, U3 and V3. Now we want to calculate these reaction forces. Now how to do it? We'll do a shifting matrix. We'll shift row 3 to row 1 position. Shift row, then we'll shift row 5 to row 2 and then row 6 to row 3. So this is the simple mathematics. I won't go into the deep how it is done. I have written the steps. The final what you will get is just the rearranging of rows which we are doing. Final what you will get will be like this: 10, then 0, 0, minus 10, 0, 0, 0, then it is 10, then 10, minus 10, minus 10, 0, 0, 10 is the third row, and 15, minus 10, minus 10, minus 5, then minus 10, minus 10, minus 10, then 20, 10, 0, 0, minus 10, minus 10, 10, 10, 0, 0, 0, minus 5, 0, 0, 5. Okay, so after doing these operations it will be like this, and this will be u2, u3, v3, u1, v1, and v2. As we have moved the rows, we have moved the columns as well. So there will be u2, u3, this is 0, this is 2 by 5, this is 2 by 5, this is v3, this is v3, 1 by 5, then u1 is equal to 0, v1 is equal to 0, and v2 is equal to 0. I'll tell you why we have done this. 2, 1, 0, and f, and this means rx1, ry1, and ry2. So why we have done this? Just to look into this problem in a different approach. If you see, if you make this line like this, you see these are unknowns. Unknowns we have clubbed one way, and since this is unknown, these are all 0, because wherever reaction will be there, this we know that displacement will not occur. Where we have the u, we are getting the reaction as well, because these of this, due to this force, we are getting the displacement values. So now we can divide into two parts like this. Means if we write it as this as K11, just writing a way of writing K21 and K22, and this is as D unknown and D known, and this is R known and R unknown. You see what I have done? We know these things. We know these D values. So we have written D. Initially we were not knowing this. So this were D unknown. Now this D we were knowing initially due to the reaction forces which are applied. So we have taken that D known. Since we didn't know the D at a point, for that point we already knew that some force is acting, and this is R known. This is R known, and we have segregated the matrix like this. Now if we see the second row, means if you see this row, we can solve this row. How? See, K21 du plus K22 dk. How can I listen yesterday's class? There will be a link for that also, he will give you. And you will get a RU. So here K21 is known. This K21 is known. This K22 is known. DK is known. RU you don't know. You don't know this RU, but yes, from previous solving, you have computed this DU. So now what you will get? I'll put this expand this and write it like this. So this is minus 10, minus 10, minus 10, 0, minus 10, minus 10, 0, 0, minus 5, and this will be 0, 2 by 5, minus 1 by 5, which we have calculated from the last last we have calculated. Then this is K22, which is 20, 10, 0, 10, 10, 0, 0, 0, 5, and here it will come as 0, 0, 0. Okay, because D known is all 0. You see, this is all 0. Now, if we solve this, we'll simply get minus 10 into 0, minus 10 into 2 by 5, minus 10 into minus 1 by 5 equals to F, means reaction, which will be, I think this will be x1. This will be x1. So you get it, you will get a reaction 1 as minus 2 units. Similarly, others, you will get a reaction as the y1 as minus 2 unit, and reaction at y2 as 1 unit. You just have to solve the equations like this, and you will get this the result. So let's see anything else is asked in that question or not. So we have to give the axial forces in all the members. Okay. Let's see what is the D part is asking us. Recover the axial forces in all the three members. Okay, let's do that also. Okay, so axial forces in all members. So let's take joint 2. We'll make it as Fx is equal to 0, which will means member 1 forces equals to 0. So where joint 2 was, so this is our joint 2. So we are making joint this member forces, axial forces, as 0. Similarly, for we'll put Fy is equal to 0. So this is the member. This is member 1 forces is equal to 1 unit. Then we'll take joint 1 and put it as Fx is equal to 0. It's just the equilibrium of the forces we are doing. When you form a the free body diagram of the member, you will get to solve it easily. So this will be F3, member 3 cos 45 is equal to 2, which will give you member 3 force. This is member 2 force, that's 2.83 units. Okay, so let's see the next problem what it says. The next problem which I have put is a continuation for the previous question. So I'll give you 2 minutes to have a look on it. I'll make the diagram of it if you have forgot. Now what it is saying. So instead of the previous question, it was like this. Now it is made vertical. Now it has made horizontal. Okay, so let's solve this. I have to write a global stiffness matrix again. 20, 10, minus 10, 0, minus 10, minus 10, 10, 10, 0, 0, minus 10, minus 10, minus 10, 0, 10, 0, 0, 0, and 0, 0, 0, 5, 0, minus 5, minus 10, minus 10, 0, 0, 10, 10, minus 10, minus 10, 0, minus 5, 10, and 15. Okay, so this was the K matrix we have formed. Now this was U1 is equal to 0, V1 equals to 0, U2 is equal to 0, V2, U3, V3, and the forces were Fx1, Fy1, Fx2, and 0 to 1. Okay, so this was the global stiffness matrix which we got at in the previous question. Now you see what has been done. We have to reduce the unknown displacements. Now what it is here, u1 is equal to 0, u2 is equal to u1 is equal to 0, this u2 is equal to 0, v1, sorry, this u1 equals to 0, similarly v1 equals to 0. Here this is not there, so here u2 is 0. Okay, that's what conditions I have put here in this. Now you can again see the stiffness matrix is similar. Since we have reduced all the constant and then form this equation, so you are getting a similar matrix. So to solve it, you again have to form a reduced stiffness matrix from this. So the similar way we have done, we'll remove 1, 2, 3. We'll remove 1, 2, 3. The known displacement, which was this, that rows I have removed. By removing this, we see the matrix which is formed is 5, 0, minus 5, 0, 10, 10, minus 5, 10, 15. Then V2, U3 and V3 equals to 0 to 1. Okay. Now I'll ask a question whether this is solvable or not. I'll give you 2 minutes to think. Can we solve this? Oh, similar matrix, what does it mean? Not similar. There's a word you are misplacing. Should be singular. Anyone else who wants to think? Okay, I'll tell that yes, he's right. That no, no, not similar. It is known as singular. It's singular. We don't say it as similar. So K matrix is singular as determinant is 0. When you find a determinant of it, see what determinant is coming. It's coming 5 to 10 into 15 minus 10 into 10 minus 5, 5 into 10, which goes to 0. This means you can't find a K inverse. Not possible. So now I'll ask you a reason. This same things you have done in the previous question and you got the solution. You got a K matrix which is non-singular. What is the reason why we are getting it as similar as here? What we have changed here? Just have a look on the in the question, the truss diagram now. What we have changed and what is the physical interpretation of this that it is not solvable? Think of it. It's a very good problem. It will clarify your basic doubts. Can you see a different can you see the difference in the both of the question? Anyone who can, if not speak, can write also. I'll wait for 2 more minutes. Have a look. It's a very basic thing you should know. Okay, no problem. I'll proceed. So why this is singular? You have a look in it. So this is your truss now. This is your truss now. This is one. This is one. This is one. Is it stable? Tell me. By putting these three external forces as reaction, is this truss is in equilibrium? Anyone who can write? Tell me. Okay, one thing you tell. Is it as raised? Okay, tell me. You can write, or you can unmute yourself also. Someone is raising hand. Someone raised hand. Is it possible for you to write or something? You can unmute yourself also. Okay, no problem. Let me ask you one more thing. Is sigma fx is equal to 0 possible here? Means here 2 is given, here 1 is given, means something like that was given, 2 or 1. Is it possible to do fx is equal to 0 here? This is rx1, this is rx2, this is ry1. Tell me, is it possible? Yes, it is possible. Why not? So see, Rx1 plus Rx2 is equal to 2. Something like this means we can change the direction of each of it. And this can be done. Means if this is 2, this can be 1 and this can be 1 in this direction. Reactions are always opposite to the force applied. So yes, it is stable in x direction. So now let's see, is it equilibrium is maintained in y direction? Think about the same way I have solved the x direction and tell me, is it possible? Is this structure stable in y direction? Is in equilibrium in y direction or not? No, sir. No. Why? Why not? Tell me why not. Tell me why not? It is not not in equilibrium. I've got one answer. Gokul Nanda, but the answer is wrong. It is in equilibrium. How it is in equilibrium? You write a sigma Fy is equal to 0. You will write Ry1 equals to 1. So whatever this 1 will be, it will be balanced by this. But is total structure is in equilibrium? What are the three conditions we require for uh, structure to be in equilibrium? This is a simple strength of material concept you need to focus on. The three conditions which we require for a structure to be in equilibrium. Two I have shown. I'll give you a hint that three are there. I know that you all know that. Two I have told. Tell me the third one. Yeah, correct. Uh, correct. This is correct. Two people have answered the correctly. Vikas and Aryan. So I'll continue. So see, you have told we have seen that fx is equal to 0 is okay. Sigma of fi is equal to 0. Now let's take the third condition, which is moment at a point should be 0. So let's take this point, and this is your reaction going in this direction. This is your reaction going in this direction. Now the external force 2, which is this, is applying a moment in this direction, and there is no reaction for it to support. You see this? So whenever this two reaction will be applied, the structure can rotate in any of the direction. Means if it is like this, it will move like this. It can move like this. Anyway, it can move. So in this question, the external forces are arranged in like this way that only two conditions of rigid body motions are countered. So we know that the rotation will is not covered in this. So this it is not possible for us to solve this structure because it is in rigid body motion. So the reason we can write, I'll write the reason so that you remember it. By changing the direction of roller, the all reactions passes through a point. Thus it will result into rigid body rotation. Hence, structure is not in equilibrium. equilibrium, therefore cannot be solved. So, what can we conclude with this? That FEM not only helps us to solve a problem, but it can tell us whether the structure is stable, is in equilibrium or not, or is it solvable or not. So, if we have seen two problems with different support reactions, one without rigid body motion, one with rigid body motions. So, this signifies that the location of these external reactions is very important. So is partial schedule in the next class problem solving after 5 p.m. It is not possible for me to reschedule it because it is being done earlier, and we are advised not to change the timing of this class. So I'm sorry for that. If this class is not convenient for you, there are two TS for this course. You can attend, but if possible, do attend a 3 to 5 live session, or I'll upload this in the uh, uh, I'll upload the lecture, and then you can watch it again. Okay, I'm working means, are you still solving it? Should I wait? Acha, you are working in somewhere. Okay, but I think the previous class had the timing from 6 to 8. That's why they have made a 2 TS so that you can have the timings of one of it matched with it. Okay, so now, since I have done a lot of numerical thing, let's solve some of the multiple choice questions now. Oh, yesterday's class was cancelled. Oh, I didn't knew that. Okay, so you have to if not possible for you, can watch this lecture, and where I'll upload it. That can be suitable for you. Let's see. They will tell you about the that previous year. Okay. So lot of work in the numerical has been done in this lecture. Now let's focus on the multiple choice questions. These questions will directly help you to solve the assignment. So let's start with the questions. You can read. Identify the dimension of element stiffness matrix for member CE for of given 2D plane frame. So first thing you have to note is that this is a plane frame, not a truss. Okay. Now this is 2D plane frame, and you are required to calculate element stiffness matrix of CE. Where is C? This is C. Anyone who want to give a try? Just go for it. I'll give it 2 minutes. It's a simple problem. One has replied. Try more. People try. One more answer I've got. I've got two answers, one from Vikas, one from Aryan, but I'm sorry to say that both are wrong. I'll wait 2 more minutes for anyone else to. Okay, I'll tell you. One thing I told you while reading the problem, that focus that this is a plane frame. What does this mean? This is not a truss, that it will have a 2 degree of freedom. What truss do? Truss cannot handle the moments. Yeah, see, because now it's correct. So this is a, if it had been the truss thing, then two here, but this is a plane frame, so one moment will also act here. So it will be something like this, and one theta you will get here, one theta you will get here. So two moments. So now three here, three here. So total 3 plus 3 is 6. So what you will get? You will get a 6 cross 6 matrix of K. Okay. So this is the problem. Now let's have one more thing to discuss in the theory part, the physical meaning of K matrix. Of K matrix. So you are forming a K matrix, you are solving a K matrix, but a simple question can be asked to you at any time, that what does the K matrix signifies? So you know the basic definition of it, that it is the force acting at each of the node when we at that node where we are applying a unit displacement. So what does the means K matrix is formed like this. This is be the jth column. So what this jth column signifies, I'll write it. Jth column of K. K means the stiffness matrix is the vector of loads that must be applied to nodal degree of freedom in order to maintain the deformation state associated with unit value of degree of freedom J, keeping all other nodal degree of freedom 0. Okay, this is just the bookkeeping thing. I'll explain you what it is. Now you see, now I will read and understand what this is. So jth column of K is the vector of loads. Yes, what we have put here, we have put here that we are giving a displacement at this, and we are getting the force at each of the nodes we are getting. So this column name signifies at which node you are giving a displacement, unit displacement, and the row which we have seen signifies that by giving the different by giving the unit displacement at jth node, what what loads or what reaction each of this node is having. So it is saying the same thing. K is the vector of loads. These are the vector of load that must be applied to nodal degree of freedom in order to maintain the deformation state associated with unit value of degree of freedom J. So when we apply a unit displacement at J, we have to make that structure in non-deformation condition, means the equilibrium condition. A certain reactions will be applied, which will be the vector of loads, which we will put here. So this is the physical meaning of the K matrix. Now we see what are the properties of this K matrix. Properties. Okay. So one thing, it should be a square matrix. Why it should be a square matrix? Because if two nodes are there, you can get a same nodes, you can get a different reactions. So same nodes, same reactions will be there. So each diagonal term of KII will be it should be positive. And why it should be positive? What KII signifies? It signifies unit displacement at I and force observed due to this unit displacement. Force observed at I due to this displacement. Now, if this is a node and you are giving a unit displacement in this direction, so it will act as, so it will give a force. You have to give a force there, so it forms a same reaction in this direction. So it always positive. The third is K should be symmetric. This is observed from the Maxwell theorem, which we see that if you are applying a load here, U12 should be equal K12 should be equals to K21. So Maxwell theorem says that if you are applying a load at 1 and getting a displacement at 2 will be equal to, when you apply a load at 2, you will get a displacement at 1 which will be equal. The fourth one is uh, if no constant is applied, if no constraint body will show rigid body motion and hence K is singular. So this is already we have shown in the problems which we have solved it. So I think this is all I have to discuss today. You, I want you all to let me know if this is session is okay or not, and or we can change something. I know this is the problems were less in this session, but I have prepared more problems. But we will do in next session so that you can do the assignment. You have seen the assignment due date is 5th, so next class will be on 1st. You try the problems with your own. Otherwise I won't discuss the problem before it. I won't discuss the assignment before the due date. But yes, in next session I'll give you a hint of each of the problem from it. I'll bring the questions which will be similar to these questions in the assignment, so it will be helpful for you. How can we ask doubt other than live classes? Other than live classes, there is a forum in the NPTEL the website. You have to ask questions there. So if possible, I'll surely reply there. Means I'll reply there. You just have to ask the question there. There's a NPTEL forum. You have to utilize that. Anything else you want to ask about this session? Means I have since it was the first class, so I tried to cover the theory one. One class can be seen. One class can be seen. Means I didn't get it, Mahesh. Mahesh, if you can clarify. Oh, this is first class. This is the first class of the TS session. Means my TS session. There are two TS sessions by two of the TS. So this is my first session. And if you have anything else you want to discuss with me, do we get recording? Yes, you will get the recording of this also. I'll upload it in the YouTube, and you will get the link of it, so you can watch it anytime. And if you watch it in the and you want to ask in the questions in the next session, you are totally welcome. Yeah, someone has raised a hand. Let me know. Nandlal, if you have a problem, you can ask. Where we get the link? You will get a link from the PMRF, means TA, this NPTEL thing. They will share you the link. I don't know if you have got an Excel sheet of it or not, but I'll post a link of the, and I'll post the link to them, the NPTEL people, and they will forward you to that. So today we have discussed a problem which was very lengthy, and if you try to solve this problem by your own, because it's a big problem, and whole of the FEM is covered in it. This is the simplest problem we can solve here. That's why the simple problem can be solved by this by hand. For complex problem, we have a FE solvers like Abacus or Athena or different software packages we have. We just have to define the geometry of our structure, and we get to the solver helps us to solve the problem. So anything, if you want to share, if you want to ask, or you want me to improve in this class, you can write it or unmute yourself as well. Or you want to any doubt you have with this lecture also, for 10 minutes I am here, you can ask it. No, can we get a FEM solver? No, FEM solver is means these are the paid software. Your college needs to purchase it, or the organization you are working in. You won't get the FEM solver. Some of the FEM solver can be free as well. You have to explore that if you want it. But these are commercially used FEM solvers. One of the name is Abacus. You must have heard of it. There you can design a plate. You can change the mesh size and everything you can do with it. Any doubt with today's session? I can see still 7 people are there. You can unmute and ask it. I'll quickly uh, move the pages of today's session, so that if you have any doubt you can stop me there. Anything you have a doubt. Okay, thanks Vikash. I'll upload this these notes also in a drive. uh, the similar the NPTEL will share you the drive link as well, where you can get these notes which I have written. so that can be useful for you to revise it. I'll be here for 5 more minutes. If any doubt in the lectures which are being uploaded by the professor, you can ask doubt as there of that as well. Next class will be on, I think, 1st of the Feb. So we'll meet at the same time, 1st Feb, timings 3 to 5. Nanlal, your hand is up. Do you want to say anything? Means you are unmuted, but your voice is not coming. You can write in the chat box as well. Tell me, Nanlal, you are raising your hand, but your voice is not coming. No, I can't hear you. You have to write it. Huh. No. Please, if you can write on the chat box, I'll be happy to help. Yeah, I'm not able to understand fully. You have to ask a question regarding which part you are not understanding. Which question, which part? Can tell me. Basic means, is it related to this problem? Means what to read? Okay. So what to read? You are getting confusion. Basic books you have to see, means I'll tell you the books related to it. Wait. There's a book, J.N. Reddy, an introduction of finite element method. You can look into it. And if you want to go to the foreign author, there's the Cook and Malkus. I'll write here if you want to refer it. J.N. Reddy, an introduction to FEM. finite element method, or I think this will be enough for you to understand the basic part. Uh, Otherwise, you have to follow the lectures and solve the assignments, and you can ask me in the TA sessions. I'll clarify the doubts. Means I want to know if you are not able to understand the today's lecture or the basic part of the FEM. Try to read it. Means get through the books or the lectures which are given. Basic part. Basic part means the FEM basics. Uh, it will be better if you understand the matrix methods of the what is basic covered in the undergrad courses. The but that is the that part is already I have mentioned in this TA session. So try solving all these questions which I have solved today. It will cover your basic part. Means if you cover this, if you solve this problem by your own, the second problem, you will get to know a lot. Is how FEM works, how you are discretizing it, how you are making its assembly of all the element and then making a global stiffness matrix, and how it is solved. So the FEM solver, what it does with a simple truss member is done in here in this question. So try solving it. Otherwise, I'll be there in the next session. Do ask me. I'll be happy to help. Okay. Will you meet you next time? Thank you.